Dear learners, welcome to the course Disaster Management Strategies. As you know, Module 17, entitled Causes, Effect and Mitigation Measures of Flood, Earthquakes and Landslide, consists of 3 units. The third and final unit of Module 17 is Unit 36, Landslide and Disaster Risk Reductions. Today, we will explore this unit together. I am Utpal Lekha, your course coordinator from Krishnakanta Hendrik State Open University. I am excited to have you with me on this journey. Let's get started. In Unit 34, we examine floods, one of the India's most widespread and recurring hazards, especially in river basins and urban areas. In Unit 35, we studied earthquakes, sudden, violent, and unpredictable events driven by tectonic forces, with mitigation focused almost entirely on reducing vulnerability through safe constructions and preparedness. Unit 36 now turns to landslide, a highly destructive slope failure hazard that is extremely common in India's hilly and mountains region, including the Himalayas, Western Ghats, Eastern Ghats, and Northeast Hills. Landslides often occur during or after heavy rainfall, earthquakes, or human disturbance, and they frequently trigger flash floods, road blockage, and loss of life. In this unit, we will cover definition and nature of landslide, major natural and human-induced causes of landslide in India, primary, secondary, and long-term effects of landslide, practical and evidence-based mitigation measures such as structural, non-structural, and community-based, real-world example and lessons from major landslide-prone regions. By the end of this unit, you will understand why landslides are often called silent disasters in hilly India and how a combination of slope stabilizations, land use regulations, early warning, and community awareness can significantly reduce their devastating impact. Let us start with definition of landslide. A landslide is the downhill movement of soil, rock, debris, or a combination of these materials under the force of gravity. This movement can be slow and gradual or sudden and rapid, such as debris flow, rockfall, or avalanche. Landslides modify the landscape through erosion and deposition. But when they occur in populated or infrastructure heavy areas, they become disasters causing heavy loss of lives, property, roads, and livelihoods. Nature of landslides. Landslides vary greatly in how they behave and how dangerous they can be. Here are the main ways they differ. First, speed. Landslide can move at very different speeds from extremely slow to extremely fast. Here are the two main types. Slow creep. This is a gradual, very slow movement of soil or rock downhill, usually only a few centimeters per year. It is often hard to notice at first because it happens so slowly. Over time, however, slow creep can cause visible damage such as cracks in buildings, tilt fences, cracked roads, or leaning trees and poles. People may not realize a landslide is happening until the damage becomes serious. Rapid flows. These are sudden and very fast moving landslides that can travel at speeds of tens of meters per second, as fast as a car driving on a highway. Rapid flows are extremely dangerous because they happen without little or no warning. They can bury houses, roads, vehicles, and people in seconds, leaving almost no time to escape. Material involved. Landslide involve different types of material moving downhill under gravity. The type of material determines how the landslide behaves and how destructive it can be. Here are the main types. Soil. Loose earth, topsoil, or regolith, that is the loose layer of broken rock and soil covering bedrock. Soil landslide are common on steep slopes after heavy rain, as water makes the soil heavy and slippery. Weather rocked, broken, cracked, or weakened rock near the surface that has been softened by weathering, such as rain, temperature changes, chemical reactions. This material is easier to move than solid rock and often forms debris, slides, or flows. Solid rock. Large intake blocks or boulders of hard rock. When solid rock fails, it usually results in rockfalls or rock slides, where big pieces break off cliffs or steep slopes and tumble or slide down very quickly. Mixed debris, a combination of soil, rock fragments, broken trees, water, mud, and vegetations. This is the most common material in many landslides, especially debris, flows, or mud flows, where heavy rain mixes everything into a fast moving, thick slurry that acts like a river of mud and rocks. Trigger. The most landslides are started or triggered by one or more of these key factors. Often combinations of triggers works together to make a slope suddenly fail. Heavy or prolonged rainfall. Heavy rain or continuous rainfall over many days shocks the slopes deeply. Water fills the spaces or pores between soil and rock particles, increasing pore water pressure. This reduces the friction that holds the slope together, making it slippery and unstable. This is the most common trigger in India, especially during the monsoon season in the Himalayas, Western Ghats, and Northeast Hills. Earthquakes. Strong shaking from an earthquake loosens soil and rock, fractures weak layers, and suddenly reduces the stability of slopes. Even moderate earthquakes can trigger landslide on already steep or marginally stable slopes. This is a major cause in seismically active areas like the Himalayas, Northeast India, and parts of Gujarat and Maharashtra. Human activities. Many landslides are made worse or even caused by people. Common human trigger include cutting or removing part of a slope, for example, for roads, railways, building, or mining, which removes support from the lower part or toe of the slope. Removing trees and vegetations, such as deforestation, which eliminates root system that help bind soil together. Overloading slopes with heavy buildings, hotels, or other structures. Poor drainage from roads, houses, or septic tanks, which lets water seep into the slope and increase pressure. Volume of material. Landslide can involve a small amount of material or an enormous quantity, depending on the size and scale of the slope failure. The volume of material that moves downhill directly affects how much damage the landslide can cause. Small local slide. This involves only a small amount of material, usually just a few cubic meters of soil, rocks, or debris. They affect a limited area, such as a single house, a short section of road, a small farm, or a narrow hillside. While they may not destroy large areas, they can still be dangerous for people or vehicles in their path and often block small roads or footpaths. Massive events. These are very large landslides that move millions of cubic meters of rocks, soil, and debris. They can destroy entire villages, bury roads and highways, block rivers, creating temporary dams that may cause flash floods when they burst, and completely change the landscape. As for example, large Himalayan landslides, such as those in Uttarakhand, Sikkim, or Arunachal Pradesh during heavy monsoon rains or after earthquakes, have buried villages, blocked major highways, and caused long-term disruption. Why India is highly prone to landslide? India ranks among the most landslide prone countries in the world. This is mainly because of young and fragile Himalayan mountains with steep slopes and weak rocks. Very intense monsoon rainfall that saturates slopes every year. Frequent earthquakes that shake already unstable hills. Growing human pressures such as road constructions, deforestation, unplanned building, and mining in hilly areas remove natural protections and destabilize slopes. These factors together make landslide common and deadly in Himalayas, Western Ghats, Eastern Ghats, Northeast Hills, and even some parts of the Deccan Plateau and coastal regions. Understanding these differences in speed, material, triggers, and volume help explain why some landslides are slow and manageable while others are sudden, massive, and catastrophic. Now we'll discuss common types of landslide in India. Landslide in India vary in how they move, what materials are involved, and how quickly they happen. Here are the most common types seen across the country, especially in the hilly and mountains regions. First, debris flow or mud flow. This is a fast moving wet mixture of soil, rock fragments, water, and sometimes vegetations that flows downhill like a thick first river of mud. It is one of the most common and dangerous type in India, especially during heavy monsoon rains. Rockfall. Individual rocks, boulders, or large blocks of rock break loose from steep cliffs or slopes and fall, roll, or bounce downhill. There is usually no continuous flow, just loose rocks tumbling down. Rotational slide or slump. A curved or spoon shaped movement where the sliding mass rotates along a concave failure surface like a spoon scooping out part of the slope. The top part often tilts backward, forming a scrap. Transitional slide. A block like movement where the sliding mass moves along a flat or nearly flat surface with little or no rotations. The material slides downhill as a more or less intact block. Creep. A very slow, continuous downslope movement of soil, regolith, that is loose surface material, or weathered rock, usually only a few centimeters per year. It is often almost noticeable. It is often almost unnoticeable at first but becomes visible over years through tilt trees, cracked walls, leaning fences, and deformed roads. Causes of landslide in India. Landslide results from a combination of preparatory factors, that is, conditions that make slopes unstable, and triggering factors, that is, events that initiate movement. In India, both natural and human-induced factors play major roles. Let us first discuss natural causes. Prolonged and intense rainfall. Heavy monsoon rainfall saturates soil, increases pore water pressures, reduces shear strength, and lubricates potential failure surfaces. This is the single most common trigger in India, especially in the Himalayas, Western Ghats, and Northeast Hills. Earthquakes. Seismic shaking destabilizes slopes, fractures rock, and triggers landslide even on moderately steep slopes. The Himalayas and Northeast are highly prone due to frequent earthquakes. For example, 2005 Kashmir earthquake triggered thousands of landslides. Increase in pore water pressures. Heavy rainfall or rapid snowmelt soaks the ground and raises the level of groundwater inside the slope. When water fills the tiny spaces, that is pores, between soil or rock particles, it creates pore water pressure. This pressure pushes the particles apart and reduces the frictions that keep the slope stable. As a result, the slope material becomes weaker and more likely to slide downhill even if the slope is not very steep. Presence of expansive or weak clays. Soil containing kaolinite, also known as Sina clay, moint murylnite, or anhydrite have a special property. They expand when they get wet and shrink when they dry out. This repeated swelling and shrinking causes the soil to crack and become weaker over time. These cracks reduce the soil strength and stability, making slopes much more likely to fail and trigger landslides, especially after heavy rain when the soil becomes saturated and heavy. Weathering and physicochemical changes. Over long periods, weathering gradually breaks down and weakens rocks and soils on slopes. The natural process happens through physical actions like temperature changes, freezing, or water pressures, and chemical reactions such as water dissolving materials or acids reaction with rocks. Weakened rock and soil lose strength, making slopes more prone to sliding, especially when heavy rains adds weight and pressure. River erosion and toe cutting. Rivers and streams flowing at the bottom, that is base or toe of a slope, constantly erode and remove materials. This undercutting removes the natural support that was holding the slope in place. When the lower part of the slope is cut away, the upper part becomes unstable and more likely to collapse or slide downhill. This process, called toe cutting, and is very common along river banks in hilly regions and greatly increase landslide risk. Weeding action of plant roots and freeze-thaw cycles. Plant roots. Tree and plant roots grow into existing cracks and joint in rock or soil. As the roots expand, they act like waste, pushing the cracks wider and deeper. This gradually weakens the slope and can eventually cause rock blocks or soil masses to break loose. Freeze-thaw cycles. In a high altitude areas like the Himalayas, water seeps into crack during the day, freezes at night, and expands. This repeated freezing and thawing acts like a natural wedge, splitting and fracturing rocks over time. The rocks become weaker and more likely to fall or slide during rain or earthquakes. Human induced causes. Deforestation and removal of vegetation covers. Cutting trees and clearing slopes removes root reinforcement and reduces evapotranspiration, increasing surface runoff and soil erosions. Unscientific slope cutting and road constructions. Road widening, hill cutting, and tunnel constructions remove toe support, create steep artificial slopes, and expose weak layers. Overloading of slopes. Construction of buildings, hotels, schools, or heavy infrastructure on unstable slopes increases load and stress. Poor drainage and water leakage. Improper drainage from roads, buildings, septic tanks, and irrigation channels infiltrates slopes, raising pore pressures. Vibrations from blasting, drilling, and heavy machinery. Quarrying, mining, and construction vibrations can trigger movement in marginally stable slopes. Excessive groundwater extractions. Pumping from wells or bore wells on slopes, lowering groundwater and can cause subsidence or instability. While heavy rainfall and earthquakes are the most frequent natural triggers, human activities, especially unscientific hill cutting, deforestation, unplanned constructions, and poor drainage greatly increase landslide frequency and severity in India's fragile hill slopes. Most disastrous landslides in recent decades have been triggered by rain but amplified by human interference. Now we'll discuss effects of landslide. Landslide cause sudden, severe destruction as well as long-lasting problem in hilly, mountainous regions of India. They can bury homes and roads in seconds, block access for weeks or months, and change the landscape permanently. The impacts are grouped into three main categories. Primary effects, that is direct damage from the moving mass. Secondary effects, that is consequences triggered by the landslide. And long-term effects, that is ongoing problems after the event. First, let us discuss primary effects or direct damage. These are the immediate results of the sliding material itself. First, burial or crushing. Houses, vehicles, people, livestock, and anything in the path can be buried alive or crushed under tons of soil, rock, and debris. Blockage of roads, highways, railway, and footpaths. Landslide often cover or destroy roads and trails, cutting off interior villages, towns, or regions from help, supplies, and markets. Destruction of agricultural land. Farmland, tea gardens, orchards, and forests are buried under debris or swept away, ruining crops, soil, and livelihoods. Damage to bridges, pipelines, power lines, and communication towers. Essential infrastructure is broken or buried, cutting off electricity, water, phone lines, and internet in affected areas. Secondary effects, that is triggered consequences. These happen because of the landslide and often cause additional harm. First, flash floods and river damming. When a landslide blocks a river or stream, water builds up behind the debris, forming a temporary lake. If the dam bursts, for example, due to more rain, it causes sudden downstream flooding. As for example, the 2021 Samoli disaster in Uttarakhand, where a rock avalanche blocked rivers and triggered massive flash floods that destroyed villages and hydropower projects far downstream. Loss of life and injury. People can be buried alive, crushed by boulders, hit by falling rocks, or killed during rescue attempts. Many deaths occur from suffocations under debris or from injuries during the slide. Displacement and homelessness. Families lose their homes, farm, and belonging and must live in temporary shelters or relocate permanently. Economic losses. Block roads, stop trade, tourism, and supply of food and goods for weeks or months, causing huge financial damage to local communities and regions. Environmental degradations. Soil erosion increases, vegetation is destroyed, river become filled with sediment, affecting water quality and aquatic life, and biodiversity suffers from habitat loss. Long-term effects. These problems continue for years or even generations in landslide-prone areas. Persistent road blockage and isolations. Repeated landslide keep major highways and rural roads closed for long periods, making remote villages hard to reach and slowing development. Reduce agricultural productivity and food insecurity. Destroyed farmland and loss of topsoil, lower crop yields for many years, leading to food shortage and higher prices. Psychological trauma and migrations. Survivors often suffer from fear, depression, and post traumatic stress. Many families permanently leave landslide prone areas, causing depopulation of villages. High reconstruction cost and delayed development. Rebuilding roads, bridges, houses, and utilities after major landslide cost government and communities huge amounts of money. Hilly regions often face long delay in infrastructure projects, education, healthcare, and economic growth. Landslides are especially dangerous in India because they often happen suddenly during heavy rain or after earthquakes, with little warning. The primary effects, such as burial blockage, cause immediate harm. Secondary effects, such as flash flood displacement, create wider chaos, and long-term effects, such as isolation, poverty, and trauma, slow recovery for years. In hilly states like Uttarakhand, Himachal Pradesh, Sikkim, Kerala, and northeast of India, landslides are a major threat to life, roads, tourism, and development. The best way to reduce this impact is through early warning, proper land use planning, slope stabilizations, and community preparedness, because prevention is far better than dealing with the aftermath. Now we will discuss mitigation measures for landslide risk reductions. Landslide mitigation in India combines structural, that is engineering based, non-structural, that is policy, planning, and regulatory based, and community based approaches. The primary goal is to stabilize unstable slopes, reduce or eliminate triggering factors, and minimize human exposure and vulnerability in high risk hilly and mountainous areas. Let us first discuss non-structural, that is long-term measures. Landslide hazard zonation and mapping. National and state agencies conduct landslide hazard zonation and mapping using geological surveys, satellite imagery, rainfall records, slope angle analysis, and soil and rock studies. This map classifies slopes into low, moderate, high, and very high risk zones. Zonation guides land use planning and prohibits or strictly restricts constructions, road building, and other development in very high risk areas. Land use regulations and slope management. Land use regulation and slope management are enforced through building by laws and town planning rules. Authorities ban or limit constructions, quarrying, and hill cutting on steep or unstable slopes. No objection certificates from geology and disaster management departments are required for any development in vulnerable zones, ensuring that human activities do not worsen natural instability. Afforestation and vegetation cover. Afforestation and vegetation cover programs plant deep-rooted species such as bamboo, vetiver, grass, elder, pine, and native broad-leaf trees on slopes. Roots bind soil, increase infiltration, reduce surface runoff, and prevent erosion. Community forestry, watershed management, and schemes like MGNREGA support large-scale plantations and slope stabilization in landslide-prone regions. Drainage control. Drainage control is a critical measure. Surface drains, subsurface horizontal drains, trenches, and check dams are constructed to divert rainwater away from unstable slopes and lower groundwater levels, thereby reducing pore water pressure and risk of failure. Early warning and monitoring systems. Early warning and monitoring systems are installed on critical slopes. Instruments such as rain gauges, tilt meters, extensometers, piezometers, and INSAR, that is satellite based, monitoring detection early signs of movement or heavy rainfall. Alerts are issued through SMS, WhatsApp groups, sirens, community radio, and local volunteers. Now we'll discuss structural measures. First, slope modifications. Slope modifications reduces the angle of unstable slopes through controlled terracing or benching where safe and geological, or benching where safe and geologically feasible. Toe cutting, that is removing material from the base of a slope, is avoided because it removes lateral support and increases instability. Retaining structures. Retaining structures provide direct support to unstable slopes. Common types include gravity retaining walls, gabion walls, that is wire mats filled with stones, buttresses, crib walls, that is timber or concrete frameworks, and soil nailing, that is driving steel rods into the slope to reinforce it. Grounding and anchoring. Grounding and anchoring strengthen weak or fractured rock and soil. Cement or chemical ground is injected into cracks to fill voids and increase cohesion. Rock balls, soil nails, or ground anchors are installed to tie together unstable masses and prevent movement. Surface protections. Surface protections seal slopes from erosions and weathering. Should create that is sprayed concrete, wear mats, geotextiles, or vegetation mats are applied to exposed surface to prevent water infiltration, surface erosions, and further weakening. Integrated and community-based approaches. Community awareness and training first. Community awareness and training programs educate local people about landslide warning signs, for example, fresh cracks in ground or walls, tilting trees, bulging soils, sudden appearance of springs, or unusual sounds. Residents learn safe evacuation routes, first aid, search and rescue basics, and relief camp managements. The Apatometer schemes and local disaster management committees play a key role in building community capacity. Build back better. Build back better is applied after major landslide. Settlement in very high risk zones are relocated to safer locations. Rebuild roads, houses, schools, and bridges, incorporate proper drainage, slope stabilizations, retaining structures, and resilience design to withstand future events. Integrated slope management. Integrated slope management combines multiple measures in high risk corridors, for example, Himalayan highways like National Highway 44, National Highway 10, Western Ghats roads, and Northeast Hill routes. Afforestations, drainage control, structural support, strict land use regulations, early warning, and community training are implemented together for maximum effectiveness. Landslides in India are largely preventable disasters. While heavy rainfall and earthquakes are the main natural trigger, most catastrophic events are amplified by human actions such as unscientific road cutting, deforestation, poor drainage, overloading slopes, and construction in unstable areas. Effective mitigation measures require a shift from reactive relief to proactive integrated slope management. Strict regulations, ecosystem restorations such as afforestation, wetland protections, engineering solutions, early warning systems, and strong community involvements are essential to save lives, protect infrastructure, and ensure sustainable development in India's landslide-prone hilly and mountainous regions. Dear learners, in this unit we began by defining a landslide as the downhill movement of soil, rocks, or debris under gravity. We explored the main causes of landslide such as natural factors including heavy rainfall, earthquakes, weak geology, and human-induced factors such as slope cutting, deforestation, poor drainage, overloading, etc. We examined the devastating effects of landslide such as burial of homes and roads, flash floods from blocked rivers, loss of life, economic disruptions, and long-term environmental damage. We also studied practical mitigation measures such as hazard zonations, land use regulations, afforestation, drainage control, retaining structures, grounding, early warning systems, and community training. India's landslide-prone regions such as Himalayas, Western Ghats, Northeast, and parts of Eastern Ghats require urgent integrated actions. The most important lesson is that landslides are often man-made disasters with natural triggers. With scientific planning, strict enforcement, ecosystem protections, and community awareness, we can greatly reduce their impact. Your role, whether as students, teacher, engineer, or citizen, is to advocate for safe slope practices, support early warning, and promote awareness in hilly areas. Prevention is far better than cure when it comes to landslide. Thank you for completing Unit 36 and Module 17. You have now studied floods, earthquakes, and landslide. Three major geophysical hazards in India. Carry this knowledge forward to build safer, more resilient communities. Stay vigilant, stay prepared, stay resilient. Thank you.